Hi class, welcome back again. I am Puan Anita teaching for Form 6 Physics Sem 2. Today we are going to look at force on a moving charge. There are three learning outcomes in today's lesson and we are going to look at the first one. The first one is going to be use the formula for force on a moving charge.
Force on a moving charge, before we go to the force, let's look at the magnetic field. If we want to draw a direction of a magnetic field, we can represent a magnetic field either by a cross or a point for the direction of the magnetic field. Okay, now what does cross and point means? It's like an arrow. Imagine like an arrow. Okay, if this arrow is point out of the page, is coming out of the page, what you see is a dot, correct? So dot means the direction of the magnetic field is out of the page. The same arrow, if it goes into the page, you will see an X. So X or cross means the direction of the magnetic field is into the page. You will see an X. If there's an X here, you will see an X, a cross. Okay? So this is the direction of the magnetic field. Point number 2. When you have a magnetic field, okay, this is a magnetic field where you can know that the direction of the magnetic field is into the page. And inside the magnetic field, there is a charge. I can put a positive charge, yeah? There's a charge, which is a positive charge. If the charge is stationary, then what can we say? The charge will not experience a or any magnetic force. Okay, point number 3. You have a magnetic field. Still, I'm going to put into the page. The direction of the magnetic field is into the page. You have a charge, which I'm going to put as a positive charge. Okay, positive charge. If this positive charge, which is Q, is moving with a velocity v, moving with a velocity v, in a magnetic field where the strength of the magnetic field is B. B is called as magnetic field strength, magnetic field strength, or is called as magnetic field of density, magnetic flux density. Okay, so what is the value of B? B is a magnitude actually. It's a magnitude of how strong the field is. So it has two names. Either it's called magnetic field strength or it's actually called magnetic flux density. So if there is a charge moving in the magnetic field with a velocity v, what will happen is this charge will experience a force. And this force is called as magnetic force. Okay, where the magnetic force will be the value of F equals to Q cross product of VB. Because if you look at the example I give you, you will notice that actually I mentioned B, B, Q. So here you can see the relationship for force will be with Q, V and B. Okay, alright. Force is a vector. And force is a vector. It has direction, magnitude and direction. Okay, so when now if I want to measure the force inside the field, I have to know the magnitude and also the direction. Okay, now let's look at the first one. Let's look at the direction of the magnetic force. How do we determine the direction of the magnetic force? By using Fleming left hand rule. By using Fleming left hand rule. Okay, so now we take our left hand. This is our left hand, correct? So here will be F, B, V. Okay, F, which is your thumb. The thumb will point to the direction of the force. And then we have this first finger here. Your first finger here will point to the direction of B. And your third finger here, or you call it as a second finger. Sorry, this is first finger, this is second finger. Your second finger will point to the direction of V. Okay, again, F, B, V. F will point to the direction of force. B will point to the first finger will point to the direction of B, and the second finger will point to the direction of V. Okay, so this is called as Fleming left hand rule. And you must understand about Fleming left hand rule, they must be angled to each other. That means 90 degrees angle to each other. Okay, so that's why you have this. This is called Fleming left hand rule. Okay, now let's apply this Fleming left hand rule in this example to determine the direction of the force. Now what do you do first, class? You just pick one first. Okay, so now I know B is into the page, correct? So I know this first finger is the direction of B. So I point it into the page. Into the page. Okay, alright, I'm going to just bring it up here a bit. I point it into the page. Okay, into the page. Now when I know the direction of B, now I find the direction of V. I point it to the direction of V, where the direction of V is in this side. So I point it same as the direction of V. Okay, so therefore my force will be in the direction which is upward. Okay, so I can draw the direction of the force upward. Okay, so this is how you determine the direction of force. A magnetic force is by using Fleming left hand rule. Okay, alright. Now, that is one thing, yeah. And you always must understand that, okay, now we know the direction, we use Fleming left hand rule, yeah. Okay, now let's look at the magnitude. how to determine the magnitude. Okay, so to determine the magnitude of the force, you use the formula F equals to QVB sine theta. QVB sine theta is a solution for the cross product. Now, what is theta? Theta is an angle between V and B. Okay, so if I have a Fleming left hand rule, alright, so this is F, this is B, this is V. Theta will be an angle between B and B. Okay, theta will be an angle between what? Between B and V. Okay, alright, now let's look at this. When, number one, when V is 0, F is 0, correct? Okay, by mathematics, if V is 0, definitely F also will become 0. Okay, I'm just wait. Alright. Okay, also, if you use Fleming left hand rule, when there is no V, there is no F. Okay, when there is no V, there is no F. That means no magnetic force acts on a charge that is stationary in a magnetic field. So number 1, support point number 2. Okay, number 1, support point number 2. Okay, now situation number 2. When theta is 0 or 180 degrees, then F becomes 0. Okay, when theta is 0 or 180 degrees, that means theta is an angle between B and V. So when theta is 0, that means this one is parallel. V and B is parallel. When V and B is parallel, that means no magnetic force. Okay, so this means that no magnetic force acts on a charge that is moving in the direction or in the opposite direction to the magnetic field. So whenever V and B are parallel, then F, there's no magnetic force. Either it's 0 degrees or 180 degrees. Okay, okay. Number 3, situation number 3. When theta is 90 degrees, okay, when theta is 90 degrees, what happens? F is maximum. Okay, so theta is an angle between B and V. So when theta is 90 degrees angle to each other, then F is maximum. Okay, right? So that is the keyword. Okay, so this is point number 3. Let me see if I left out anything. Okay, that's all. Alright, okay, point number 4. Point number 4. Okay, point number 3, you will notice that we are actually using a positive charge in this example. Point number 4, I'm going to use a negative charge. So I have a magnetic field which is pointing into the page. Okay, and then I have a negative charge which is moving with a velocity v. Okay, so what will happen? This is a B. What will happen? This is a Q, charge Q. This charge, this negative charge will experience a force. Okay, what force? Magnetic force. Okay, and magnetic force means it has what? F equals to Q cross product of V times B, which the force we have magnitude and direction. Okay, now for magnitude we still use the same formula, F equals to QVB sine theta. Okay, but for direction will be a bit different between a positive charge and a negative charge. Now what will the difference be? The difference will be F equals to negative Q. Okay, I'm just going to put here V times B. So that's why I have to put a negative there. Understand? Okay, so the formula there will change here, will become negative. Will become what? It will be having a negative. Okay, what does it mean? The mean that the direction will change. Okay, let's look at this example here. Still, we have to use Fleming left-hand rule, yeah, for the direction. Okay, now let's look at this example here. Okay, so now first thing, what do we have? We have three quantities there. We have a B, we have a V, and we want to find F, the direction of force. Okay, still we use Fleming left-hand rule. Now, first thing we fix for one first. Okay, B is into the page. Okay, I'm just going to lift up this up a bit. B is into the page. Then we go for the next quantity where the direction of V is to this side. So, V. Okay, V. Okay, then where will the direction of F be? The direction of F will be upward. Okay, the direction of F will be upward. So that means here, the direction here is upward. But negative upward means you reverse. You reverse. When you reverse the direction or you flip, the direction will be downward. That is what happens for negative charge. Okay, so here you get upward, you negative. That means opposite of upward. That means you reverse the direction of the force. Then you will get the direction of your force downward. So that is the difference between a negative charge in the magnetic field and a positive charge in the magnetic field. So when you use the Fleming left-hand rule, the direction will change. Okay, the direction will change in order because of its negative, charge negative. You just reverse. Okay, alright. Okay. And another one more thing I just want to let you all know, just for your extra information, when you use FBV, actually this V is in the direction of a positive charge. That is the reason why you reverse. Okay, so I don't want to make you reverse at V. I want you to find the F and reverse the F. Okay, so that's what I did. I find the direction of F, which is supposed to be upward. I reverse it when it becomes a negative. Okay, when it's a negative, not when it's become a negative, when it is a negative. Okay, so this is the four important point that you have to know. The first point, you have to know about the direction of the magnetic field. We have cross and we have a dot. Cross means into the page, dot means out of the page. Okay, and then number two, a stationary charge inside the magnetic field will not experience a magnetic force. And number three is about a charge which is inside the magnetic field and moving with a velocity v. okay, then it will experience a force, and then we want to know the force, we have to know the magnitude and the direction. Okay, so direction we use Fleming left hand rule. Okay, and then number 4, if that charge is a negative charge, then you slip or you reverse the direction of your F. Okay, all right, so that is all, class.
These are points to remember. The direction of the magnetic force depends on the sign of the charge. Either it's a positive charge or it's a negative charge. And to determine the direction of the force is by using a Fleming left-hand rule, where your thumb represents the direction of the force and your first finger represents the direction of the magnetic field and your second finger represents the direction of V. And they are each right angle to each other. But when it is a negative charge, then when you use your Fleming left-hand rule, you will get your direction of your force. You have to reverse the direction of force in order to get the exact direction of force for the negative charge. That is the reason why you can see a negative here compared to the one that is in a positive charge. Our second learning outcome for today's lesson is to use the equation to define magnetic flux density. The definition of magnetic flux density. Magnetic flux density or magnetic field strength is a vector field which we identify using the symbol capital B and which has a SI unit of Tesla. This magnetic flux density, the definition is taken from the formula F equals to BQV sine theta. This definition is only used for a charge that is moving with a velocity v. The definition of the magnetic flux density or magnetic field strength of a magnetic field is the force on a charge of one coulomb moving with a velocity of 1 meter per second at a right angle to the magnetic field. Right angle means theta is 90 degrees. Tesla. What is the definition of Tesla? Tesla, symbolized as capital T, is the standard unit of a magnetic flux density. A magnetic field of 1 Tesla is quite strong. It is named in honor of Nikola Tesla. The definition of Tesla is actually the magnetic flux density or magnetic field strength of a magnetic field is 1 Tesla, means 1 T, if a charge of 1 coulomb moving with a velocity of 1 meter per second at right angle to the direction of the magnetic field experience a force of 1 Newton. The third learning outcome for today's lesson is to describe the motion of a charged particle parallel and perpendicular to a uniform magnetic field. The fact is, since the magnetic force is perpendicular to the direction of travel, which is the direction of V, a charged particle will follow a curved path in a magnetic field. The particle continues to follow this curved path until it forms a complete circle. This is a fact. Now, we want to describe the fact. So let's follow the lesson.
Okay, now for the next one, class, all right, I draw a magnetic field. Okay, I'm just going to draw a magnetic field which is into the page. The direction of the magnetic field is into the page. Okay, next, I have a positive charge inside the magnetic field. mass m, charge q, moving with a velocity v. The strength of the field is B. Okay? And this B class, it is uniform. Uniform means the magnitude and the direction is constant. Okay? Is fixed. Alright? Okay. So what happens is, based on the concept that we studied before this, when a charge is inside the magnetic field, the charge will experience a force. Okay, the charge will experience a force. Okay, now this force, now we want to draw the direction of the force. Now when we want to draw the direction of the force, what must we do? We must use Fleming left hand rule. Okay, so let's use Fleming left hand rule. Okay, first thing, okay, F, B, V. Now we fix B first. B is into the pitch. The direction of B is into the pitch. Okay, and then V is in this direction. So the direction of force will be upward. Okay, into the pitch, right angle to each other. Okay, so V is in this direction, B is in this direction, so F will be upward. Okay, alright, so the direction of force will be upward. Okay, so what happens is, class, F is perpetually at right angle to the velocity V. Okay, now when positive charge is moving, when the positive charge is moving, the F is upward, the F is upward. So what will happen is, the force F will cause the particle to move in a circular path. You see, as the V is going here, the force is upward, so it will make the positive charge to move in a circular path. Alamak, tak selaras. Okay, anyway, this is not okay, let me draw back again. Okay, let me see. Okay lah. Okay, alright, so then, okay, I give you an example. At this particular point, it will be V. The direction will be to the center, F, the direction of force. Then here is V. Then the direction of the force will be in this direction. Then when it's here is V. Then the direction of force will be to the center. So as you go on, it will be something like this. All to the center. All to the center. So this is the center. Okay. So it's a concept of a circular motion. So when a charge, the important concept is, when a charge is inside the magnetic field, the charge will be exerted by a force, and that force will cause the particle to move in a circular path. So you have to use the concept of circular motion. Okay, so what is the force? F equals to QVB, the magnetic force. Okay, F is equals to QVB. And the force F is towards the center. So the force F is the centripetal force. Okay, if you remember the concept of your circular motion, centripetal force are force that is directed towards the center. Okay, so in this case the magnetic force is the centripetal force. Okay, the magnetic force, this is the magnetic force, is the centripetal force. Therefore I can say that I'm going to call this Fm, yeah, to tell you it's a magnetic force. And centripetal force Fc is equals to mv square over r. Centripetal force got three formula. You can use whichever formula you want to use. Okay, but here I'm going to use mv square over r. Another two formula we have is mr omega square, mv omega. But I'm going to use mv square over r. So the concept here is the magnetic force is the centripetal force. Okay, important, yeah. The magnetic force is the centripetal force. Okay, and what is the magnetic force? Is QVB, and what is the centripetal force? MV square over R. Okay, and then from here you want to find whatever quantity you want to find, or you want to analyze any quantity, you can go ahead and analyze. So now what I'm going to do is I'm going to analyze the quantity of the radius of the circular path, which is from the center to here. Okay, to the circular, the radius. I'm going to find that value. So I can do that, class. How do I do that? From the concept. It's all start from the concept. So from the concept, the radius R will be mv over qb. Okay, you solve this, you get R equals to mv over qb. Okay, and you will realize that the radius is directly proportional to the velocity. Correct? Is directly proportional to the speed, is the magnitude. Correct or not? Because radius is a scalar, so we talk about the speed, which is the magnitude of the v. So it's directly proportional. Okay, so when we say it's proportional, that means they are dependent. Alright, okay. Alright, next, what else can we find? We can find the period of the circular motion, the period. Okay, let's look at the period of the circular motion in this example. Alright, okay, first thing, we know S is equals to R theta. Okay, theta is the angle, S is the circumference. Okay, alright, so in this case S equals to R theta. So S is equals to R, angle theta in radian will be 2 pi. So it's 2 pi. Okay, complete circle will be 360 degrees, which 360 degrees is equals to 2 pi. Okay, alright, now V is equals to S over T, the definition of velocity. Correct? So in this case, to apply to this example, V is equals to S as the distance taken. So from here until here is 2 pi r. Correct? So 2 pi r. And T is the period, time taken for one complete circulation. T is a period. So therefore T is equals to 2 pi r over V. Okay, and R, I already know R from this formula, so I substitute R here is 2 pi. R is mv over qb. So I get T equals to 2 pi m over qb. Okay, now the question is, what should I understand from this concept? What I should understand is, class, the first thing, point number 1, when a charge moves in a magnetic field with a velocity v, the charge will move in a circular path. Okay, you remember when we studied about electric field, when a charge moves in the electric field, the charge will move in a parabolic path. But in a magnetic field, the charge will move in a circular path. Concept number 1. Concept number 2, when the charge moves in a circular path, the direction of the force is towards the center. And when the direction of the force is towards the center, the force is the centripetal force. So the concept there is the magnetic force is the centripetal force. Concept number 2. Okay, and from there you can find whatever quantity you want to find. I just gave you a 2 example, which is to find the radius of the circular, and also the time taken for one complete circle. You can also find frequency, you can also find B, you can find anything you want to find. Okay, but the most important part they want you all to understand this is that 2 important fact, that when a charge is inside the magnetic field, it moves in a circular path, and number 2 is the magnetic force is the centripetal force. So that's why we get Fm equals to Fc, and you can substitute your Fc with anything, but in this example, anything means in a sense of that 3 formula la, class. Okay, here I substitute with mv square over r. You can also substitute with mr omega square. You can also substitute mv omega. Okay, and you can find your omega also if you want. Another thing I want to explain is, when the charge is moving in the magnetic field in a circular path, okay, so it keep on moving and it's keep on going, right? As it's move, it going circular, right? So it will form a spiral. It actually will form a spiral as it moving forward in the magnetic field. Okay, as it going V and it's moving in a circular path, and then it will keep on moving like a form of a spiral and moving forward. Okay, all right, so that is all, class. Thank you.